So when we're doing this, you have to have real chemistry happening. And here's what would happen at the dance sometimes. Sometimes we'd be out there dancing, and it got really crowded on that dance floor because it wasn't a giant space, and there were a lot of people there taking these classes. So it would get really crowded when you're out there, and then as the evening progressed, I would notice sometimes that the dance floor wasn't so crowded. But if you looked around at the bleachers, you didn't see people sitting on the bleachers. And so this was kind of a puzzle to me. Why is the dance floor not so crowded? So one night, my sister and I were there, and the time was up, so I went out to the curb where Dad was picking us up. And I walked to the car. My dad says to me, "Where's your sister?" Well, I don't know. He's like, "Well, go in there and find her." I'm like, "I don't know where she is. She's supposed to be out here. She's not my problem. Go in there and find your sister." So I go in there and I look around. She's not on the dance floor. She's not in the girls' bathroom. Finally, I walk around the back side of the bleachers. And here's a whole bunch of young couples back there, and that's where the real chemistry was going on, all right? They had left the dance floor, and there's all kinds of hanky-panky going on behind the bleachers, and my sister's back there. And I walk up to her. I'm like, "Stop that. Let's go. Dad's outside waiting." She's like, "What are you doing out here?" And I'm like, "I'm looking for you. Dad sent me to get you. Let's go." She was in a lip lock with this guy, Bob Lewis. I didn't really like the guy, but anyway, not my business. So we go out. But that was removing students from the dance floor. And when the chemistry happens, you are removing ions from solution. The ions are hooking up, and they're either making a solid, a gas, or a weak electrolyte. So the first type is the formation of a solid or a precipitate. We say that it makes a precipitate, that's a solid, in the bottom of the beaker, and we use the subscript S to mean solid. This is sometimes confusing because if it is soluble, we use the subscript AQ, meaning dissolved in water. So S means solid, not soluble. So there are certain ions that when hooked up, they make soluble compounds, things that dissolve. Nitrate, acetate, chlorate, perchlorate, ammonium, alkali metals, that's the hydrogen family. Everything in that list on the alkali metals will hook up and it will dissolve readily. Sulfates usually dissolve. However, if sulfate is hooked up with lead-2, mercury-1, calcium, barium, or strontium, it does not dissolve. Chlorides, bromides, and iodides are generally soluble unless they're hooked up with silver, lead-2, or mercury-1. These are the solubility rules. This is something that you have to learn. Memorize, I guess, is the word you like. But you have to learn this so that when you glance at something, you know whether it's soluble or not. On this list, the ions make compounds that are generally insoluble, unless these things on this list are hooked up with something from the soluble list. So hydroxides and metal oxides are typically insoluble unless they're hooked up with calcium, barium, or strontium. Rob? Okay. Carbonates, sulfides, sulfites, and phosphates make things that are insoluble. But if you want to get them in solution, you hook them up with something on the previous list. So this list gets things into solution. This list takes things out of solution. So when you think about this, when I was in high school, after those lessons, if you wanted to go to the dance in high school, you had to have a date. Then once you got to the dance, you could dance with whomever you liked, maybe even leave with somebody different. It's kind of rude, but it happened. So I think of the things on this list as your date to the dance. Okay? The alkali metals are cations. Anytime you want to get an anion in solution, you hook it up with an alkali metal and it will dissolve. So you think of like lithium, sodium. Sodium is like the girl next door. It's cheap and it's readily available. So anytime you want something in solution, you hook it up with sodium and it gets in the beaker, it gets to the dance. If you need to get a metal in there, you use nitrate. Okay? It's cheap and readily available. And anything hooked up with nitrate will dissolve, and then you can have those things in there to do the real chemistry. So, soluble list, insoluble list. If you mix soluble with insoluble, soluble wins. So let's look at a couple of examples now of double replacement or metathesis where we're forming precipitates. Silver nitrate and sodium chloride. We trade partners and we make silver chloride. Now, when you're doing this, you always write the proper formula. So you write the proper formula. Silver's a +1, chloride's a -1. We write the proper formula. And sodium nitrate, NaNO3. Again, this is why it's so important to know those charges on the ions. Now we've written the proper formulas. Now we balance the equation. This one is balanced. Now we add subscripts for physical states. Put a solid here and an AQ here. This is what you're going to have to do on the next quiz and on the test. You're going to be told, complete these equations, balance them, and include proper subscripts. So that's what you're going to be doing in the next section. Cadmium nitrate and sodium sulfide. We trade partners. We make cadmium sulfide +2 -2, and we make sodium nitrate, NaNO3. Sodium's a +1, nitrate's a -1. I do not write Na2NO3 2. This is a common mistake I see students do. You do not do that. You write the proper formula. Now, because there are 2 nitrates here, we need a 2, and we need 2 sodiums there, which we have. So now we have a balanced equation. Now we're going to put in our subscripts for physical states. Sulfides are insoluble, so we have cadmium sulfide solid, and sodium and nitrate are on the soluble list, so we make those aqueous.